Good evening, everyone. Is my voice audible and are you able to see the screen? Can someone confirm?
Yes, can see the screen and your voice is audible.
Okay, thank you. Thank you
Audible.
so much. Okay, so we'll start off with the class. So, welcome back, everyone, to the NPTEL online course on the water and wastewater treatment. So, today we'll be discussing the questions related to the contents of week 11. And as you all know, the course instructor is Dr. Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Saha, and I am a PMRF scholar at the Department of Civil Engineering at IIT Madras. Okay, so let us quickly see the contents of week 11. So in week 11, we discussed about adsorption and the various mechanisms of adsorption and how activated carbon is used in the process of adsorption and what do you mean by GSE breakthrough, and then various isotherms related to the adsorption, like the linear, Langmuir, Freundlich, and the BET isotherms. Then we also discussed about the ion exchange processes, the different type of ion exchangers, and the selectivity of this uh, ion exchangers. And then we talked about filtration processes like the nanofiltration and the reverse osmosis in particular, and what are the various parameters and properties related to them. And finally, we discussed about the process of aeration, where we talked about the removal of ferrous and manganese, okay, and the various methods related to that. Okay, so this was the overview of small topics, but all related to the water treatment. Okay, so we'll start off with the question answers. So let's solve the first problem, rather very easy problem. So it says that calculate the water recovery in percentage in the following RO process data. Permeate flow is 200 meter cube per hour, feed flow is 250 meter cube per hour, and the flux considered is 18 LMH. So LMH is liters per meter square per hour. So you have to tell me what is the water recovery in percentage. So you can just tell me. I think not much calculation is required. So yes, that is the correct answer. So when we talk about water recovery, it's about how much water we are able to recover as permeate from the feed. So it's nothing but the ratio of the permeate flow to the feed flow. So 200 by 250 will be 80%. Okay, so permeate flow by feed flow is the water recovery. Another important parameter in the filtration processes is the what is the other important parameter? Can someone tell me in filtration processes that we generally check apart from
Rejection.
yeah, rejection ratio. Rejection ratio is the other one. So it depends on the concentration of contaminant in the permeate to the concentration in field. How much has been rejected? So it's 1 minus concentration of permeate divided by the concentration of feed. Okay, so another parameter. Okay, moving on to the next problem. It says that adsorption of toluene onto activated carbon obeys Freundlich isotherm equation, where C, that is the concentration, is in milligram per liter and Q is in milligram per gram given below. So we have the relation there. A solution at 25 degrees Celsius contains 0.85 milligram per liter of toluene is to be treated in a batch process to reduce the concentration to less than 0.03 milligram per liter. The required activated carbon dose in milligram per liter is. So the Freundlich isotherm is given. So equation is given and the initial and the final concentration of toluene is also given. So you have to find out how much activated carbon will be required for the removal. Please try to solve it. Yeah. So please try to solve this. So I hope you are aware of the Freundlich isotherm equations, like uh, what do they signify and how does it help to understand the adsorption process. So are you aware, like what does the Freundlich isotherm equation signify? Anyone who would like to say, like what does it really tells? So like Freundlich isotherm, we have different isotherms, Langmuir isotherm, we have BET isotherms. Okay, so what do they tell about the absorption process? We have an equation here. So what does this equation signify?
It's like the Langmuir, which was dependent on the fixed sites. The absorption happens on this fixed sites, but in the Freundlich absorption, it doesn't happen only on this fixed sites, but it actually depends on the concentration.
No, okay, you are talking specifically about the particular isotherms. I'm just asking, like, what do these equations represent? Like, what is Q here?
Q is the amount that has been absorbed
Yeah, amount absorbed.
of
Absorbed,
the solid. Yeah, I guess it was from the solid.
yeah, per
Uh,
unit of the adsorbent. Okay, so that we
yes.
have to keep it in mind. So milligram per gram. So it might look like unitless value, but it is milligram per gram, where milligram is the signifies the contaminant removal, and gram is that of the adsorbent. Okay. So anyone with the answer?
Yeah, Q is 20.4052 milligrams per gram.
Yeah, that is right.
And and for C, or C initial equals to CF plus Q into C of that carbon which is required, I guess it's like 0.0401 grams per
Yes.
liter.
Yeah, yeah, that is correct. But here they are asking in milligram per liter, so just multiply it with 1,000. So that thing you have to
So
take
in that case, it's like 40
40,
point.
41.1. Yeah, that is right. Okay, for others, let me solve the question. So I think question number 2. Just a minute. Yeah. So we have been given that Q toluene, that is the contaminant here, follows the empirical equation of 73.4 into the concentration of toluene in the system to the power 0.365. So just if we put the concentration, the equilibrium concentration in the end, so it is given as 0.03. So 0.03 to the power 365. So the Q we will get as 20.41 milligram per gram. So milligram of contaminant per gram of the adsorbent. Now we will apply mass balance on the contaminant to get the dose of activated carbon. So the reason we are applying mass balance is that the total concentration of the contaminant will be present in the entire, will be intact. Okay, it is not getting degraded. It is just coming out from the liquid phase. Some part is getting adsorbed on the solid phase. Okay, so that is the only change that is happening. Okay, whereas there is no degradation, there is no loss of mass of the contaminant. So that thing you just have to keep it in mind. So the so we can say that the total concentration of toluene, okay, so C total of toluene will be equal to the concentration of toluene, okay, in the system, okay, in the whatever uh, uh, flask they are doing it, into the Q of toluene that represents the amount that is adsorbed on the adsorbent, and then the dose of the adsorbent, that is activated carbon AC. Okay, so the total toluene in the system, that is the initial concentration, we know it's 0.85, and the final concentration is 0.03, plus some amount is adsorbed. So that adsorbed around amount is 20.4 milligram per gram of adsorbate. So how much gram of adsorbate we will multiply? So that is uh, the dose CAC. Okay, so now concentration of activated carbon will be coming out as 0.0401 gram per liter. So based on the units, it will be gram per liter. So ultimately, if you change it to milligram per liter, it will be 40.1 milligram per liter. So that's how you have to solve this. Okay. So I hope this is clear. So these are all empirical equations derived. Okay. So it can change. So based on our system properties, these values can change. So we have to come up with the equation when we do the designing. Okay, so 40.1 is the right answer. Next. I hope that was clear to all of you. If you have any doubts, you can please let me know. Next, what match the following isotherms with their respective descriptions. So we have Langmuir, linear, Freundlich, and BET isotherm. So please let me know what is the correct match. B. Okay. Anyone else? B. Yeah. So B is the correct answer. So for Langmuir isotherm, we know that it is assumed that only one layer or monolayer of adsorption will be there. So that's how we define the Langmuir isotherm. Then for linear isotherm, we say that the solid phase concentration is linearly dependent on the concentration of compound in water. Okay, so there is a linear relationship between the amount which is there in the solid versus the amount which is there in the water. Then Freundlich isotherm, we say that it is a better fit for granular activated adsorption. So in the previous example also we saw, okay, we use the Freundlich isotherm because it's a better fit for the activated adsorption. And then the BET isotherm, so in that we assume that there are several layers of adsorption. In Langmuir only monolayer, whereas in BET we assume that there are several layers. Okay, so B option is correct. Next, select the correct statements regarding reverse osmosis theory. So it says that chemical scale fouling in membranes occurs due to the increased concentration of ions in concentrate. Solute rejection is lower for highly charged molecules but higher for larger molecules. Membrane material is susceptible to biological degradation and degrades with free chlorine concentration below 1 milligram per liter. Volumetric flux of water is given by Jw is equal to Kw into delta P by minus delta pi. So which of the options are correct? So which of the options do you think are correct here? Okay, so C is not correct, we are saying. Okay, so let us go by the statements one by one. So first one says that chemical scale fouling in membranes occurs due to the increased concentration of iron in the concentrate. Yeah, so that is true. So chemical scale fouling is due to the concentration of iron, more and more concentration of iron. So it is directly related to the fouling. Then solute rejection is lower for highly charged molecules but higher for larger molecules. So solute rejection in general we will know that it will be higher for larger molecules, okay, because larger molecules will not be able to pass through, whereas highly charged molecule will also be rejected more, okay, based on the electrostatic principles or the Donald dialysis effect. Okay, so highly charged molecule will be rejected more. It's not less, it is more. So option B is incorrect. Then membrane material is susceptible to biological degradation and degrades with free chlorine concentration below 1 milligram per liter. So that is not true. Membrane materials in reverse osmosis theory, these are susceptible to biological fouling. Okay, not biological degradation, but biological fouling, because the microbes can get attached to that. Okay, and if they are getting the nutrients, they will be growing, or they will secrete some EPS kind of things. Okay, which are extracellular polymeric substances, and then it will foul the membrane, but it will not undergo membrane degradation as such. Okay, so option C is also not correct. Then volumetric flux. So as you know, flux is will be always directly proportional to the pressure applied, be it the osmotic pressure or the external pressure applied. Okay, so that's why JW is equal to the change in pressure. Okay, that delta P is the transmembrane pressure here.
Sir, is it like membrane material is susceptible to biological biofouling, so it's not degradation?
Yeah, yeah, yes, yes. So membrane
Okay,
material is,
but yeah, I have noted here from the videos like it was membrane material is susceptible to biological degradation and degrades with free chlorine concentrations above 1 milligrams per liter.
okay, above, like where you have come across this one?
I've heard this in the videos, like it was in the properties of RO,
Okay,
and that was one point in the slides.
okay. Yeah, okay. So yeah, they are telling that degrades with the free chlorine concentration above, right? Not below. Okay.
Yes, above.
Okay, that may be the case, but in general, membrane materials are susceptible to biological fouling. Okay. So as such, the membranes are, we cannot say directly that it will degrade biologically, uh, but yeah, it will be susceptible to fouling. Okay, but yeah, free chlorine, if concentration is going very high, then it can cause issues with the membrane. Okay, so the second part is different. I was talking about the first part. Okay, so that's what. And also it depends on the type of membrane. Okay, whether it's an organic membrane or inorganic membrane. Okay, so based on that, the amount of biological fouling, or even if you're talking about degradation, it will change. Okay, what kind of material are being used for these membranes?
Yeah, maybe if it's like polyamide derivatives because they're hydrophobic and they're
Yes.
very reactive toward chlorine that might damage the membrane
Yeah,
at
yeah,
some point.
yeah, yeah. Okay, so yeah, moving on to the next problem. What does sequestration mean in reference to iron and manganese removal? Okay, So we are talking about sequestration here, not precipitation. Okay, so both are different things. So please try to answer accordingly. Yeah, someone has already answered it correctly. So it is the use of phosphates, okay, which are added to water, and then they will bind the iron or manganese in the soluble form itself. Okay, it will be there in water soluble form, not in a precipitate form. Okay, and they do this because they want to make it non-reactive, okay, such that they will be stabilized and soluble in soluble form, and they don't precipitate out, okay, from the system. So that is something known as sequestration, not precipitation. So option B is the correct answer here. Okay, phosphates are added to water to bind the ferrous or manganese to make soluble in water. So phosphates like polyphosphates or sodium silicates are used, and they prevent it from oxidizing or precipitating out of water. Okay, which can cause some kind of other staining or other problems. Next, the oxidized forms of ferric and Mn4 plus are highly soluble in water. Chemical oxidation is not effective for removal of ferrous because it forms aqueous complexes with norm, that is a natural organic matter. Green sand or glauconite can be said to behave as an ion exchanger to remove ferrous and manganese. At neutral pH, ferrous gets oxidized and precipitated out, but manganese does not get precipitated. So, which of the options are correct? So, what will be the correct answer here? Can someone tell? So, here we are asking about what is the correct statement. So, which of the statements are correct? So here, except option A, all the others are correct. Okay, so you have rightly mentioned. So B, C, D all are correct. So I'm not going through that. Whereas A, the oxidized form, that is the ferric and the Mn4 plus, are highly soluble in water. That is wrong, because these two phases will precipitate out as ferric hydroxide or manganese dioxide. Okay, so these oxidized form are poorly soluble at neutral pH. Okay, so option A is the only incorrect option, whereas B, C, D are correct. Because yeah, if you talk about the second option, the chemical oxidation might not be effective because yeah, ferrous will form some complexes with the natural organic matter, which it interferes with the oxidation. Okay, so like that, the other two are also right. Okay, so I know these topics are a bit theoretical, but you try to understand the oxidation states and their behavior at different pH. Okay, then you will be able to remember this. In the context of activated carbon, what does activation refer to? Heating of carbonaceous material in absence of oxygen to liberate carbon, exposure of carbonized material to steam, increase in surface area of for sorption, chemisorption of coal and ash to the surface of carbonaceous material, formation of pores and fissures. So what does activation mean with respect to activated carbon? Just think about the term activation. Like, when do we say like we are activating some compound? What does that mean?
Sir, I think D.
D, D or B? So activation means we do activate a carbon or anything to make the performance much better, right? We will like to make it more better performing material. So that's why we tend to activate any material, right? So in that case, anything which can increase the surface area or provide more sites for adsorption, okay, make it more chemically active, okay, will come under the activation. So here if you see exposure of carbonized materials to steam, if you expose any carbonized material to steam, what will happen? That the porous structure will come out. Okay, the less ordered carbon will be removed. Okay, then increase in the surface area of sorption. That also means activation. Then formation of pores and fissures. So if more porous material will be there, the surface area will increase. So ultimately it will get activated. Okay, more sites for adsorption will be there. So option B, C and D and E will refer to increasing the performance of the carbon. Okay, so that's why it is called as activated carbon. Okay, so the correct options are B, C and E, right? I hope this is clear. Whereas heating of carbonaceous material in absence of oxygen to liberate carbon is a different process. I think it is called as carbonation. Okay, then chemisorption of coal and ash to the surface of carbonaceous material. So it means you are already occupying the material adsorption sites with coal and ash. Okay, so that is not activating. Okay, we have to increase the performance, make it better. Right? I hope this is clear to all of you. Next problem. Select correct statements regarding ion exchange. It is easier to regenerate weak acid resins compared to strong acid resins. There is a stronger attraction to singly charged ions due to smaller hydrated radius. In a resin column, the exchange reactions begin to saturate the lower levels before the upper levels. HCl is used as a regenerant for cationic resins. NaOH is used as a regenerant for anionic resins. So which of the options are correct?
Sir, BDE.
Sorry, B, D, and E. Okay. Anyone else? A, D, E. Okay. So let's see the first statement. It says that it is easier to regenerate a weak acid resin compared to a strong acid resin. So obviously it will be easier because why we say it is a weak acid resin? Because the ions are not strongly attracted or not strongly attached. Okay, since it is a weak acid resin, then it will be easier to regenerate the weak acid resin. Okay, because the electrostatic uh, attraction will be weaker in that. Okay, whereas in a strong acid resin, the electrostatic attraction will be much higher. Then coming to the second statement, there is a stronger attraction to singly charged ions due to smaller hydrated radius. So in that statement, it is true that for any smaller hydrated radius, it will be of more attraction, but charges have the higher affinity. Okay, if it is a highly charged ion, then it will have more affinity even if it has a higher hydrated radius. Okay, so charges also matter. Then in a resin column, the exchange reactions begin to saturate the lower levels before the upper levels. So this is false because in resin column, the flow will happen from the top to bottom. So obviously the top levels will be saturated before because they will be used up in ion exchange before. Then the lower levels will be filled up, will be used up. So that's why option C is also false. Then HCl and NaOH, okay, they are used for the regenerant of the cationic as and anionic respectively. So D and E are correct. So here option A, D and E are correct. Okay. So always remember charge matters more for the attraction, and then in an ion exchange column water flows from top to bottom. So that's why the top ions will be saturated first. Next. In general, soil possesses cation exchange capacity due to the presence of negatively charged K particles. True or false? So this is very direct. There is not much concept behind it. So obviously, because of the presence of negatively charged clay particles, the cations or the positive charges will be attracted. Okay, so it is true. Okay, again, so in this exercise, most of the problems are like find the correct statement. Okay, so it's all mostly theoretical. Select the correct statement regarding chemical and physical adsorption. If the pore volume is taken up by pores of different sizes, then efficiency of adsorption is decreased. Physical adsorption, the forces of attraction include only physical forces and exclude covalent bonding. When chemical adsorption occurs, the media generally can accumulate multiple molecular layers. Physical adsorption is exothermic process, while chemisorption is endothermic process. Physical adsorption is generally reversible, while chemical adsorption is generally not reversible. So please try to let me know the correct answers. Okay, any other answer? Anyone else would like to guess any answer? So the given answer, somebody already answered. So one of the option is incorrect. So would you like to modify your answer? One of the option is incorrect.
I'm sure option B and E are correct,
Okay.
but what about the A? If the pore volume is taken up by pores of different sizes, then efficiency of absorption is decreased.
Yeah. So
I
what do you
guess it's
think?
correct.
Yeah. So
So
see, if the pore volume, if more and more, I would say, molecules are coming and filling up the pore volume more efficiently, don't you think the adsorption will be increased? The efficiency will be increased, right? If there are various different sizes. Okay, because there will be no pore left there.
yeah, now I got the point. Yeah,
Yes,
it's wrong.
got the point? Yeah. So the adsorption efficiency will increase, right? Because we want more contaminant to come and take up the pore volume. And the pore volume is not uniform, right? There will be various sizes of pores. So we need various sizes of molecules or particles to fill up that volume. Okay, right? So absorption will be increased. Then option B is definitely correct because it includes only physical forces for physical adsorption and covalent for other things. Then if chemical adsorption is taken, then a particular bond will be formed. Okay, so that bond, if that is formed, then the space is already used up. So there will be a monolayer already formed. So there cannot be any more further layers for adsorption be formed on the material. Right, so option C is incorrect. Then D is also incorrect because both of them are exothermic or endothermic. Why D is incorrect? Because both are relatively exothermic. Okay, then physical adsorption is reversible, whereas chemical adsorption is not reversible. So that is also true. So option B and E are the only correct options here. Okay, So again, the same question is coming. Activation of carbonized material involves exposure to steam, pyrolysis, formation of pores and fissures, all of the above. Okay. So here the different term is only pyrolysis. So what is pyrolysis?
I guess it's like heating this carbon, which kind of removes the organics and left. We're just getting this carbon, but it's not activated.
Yeah, so
It's
what is the key
in the
term here? In
absence
pyrolysis, what is the key thing?
Absence of oxygen.
absence of
Yes, absence
oxygen.
of oxygen. So that is something known as carbonation. Okay, that is not activation. So option A and C are correct. Okay, so pyrolysis does not activate the carbonized material. Okay, so option A, exposure to steam or the formation of pores and fissures is related to the activation. Okay. Again, which of them are correct? Granular activated carbon is a heterogeneous media for adsorption. Only natural and not synthetic organics can be removed by granular activated carbon. The more hydrophilic a compound is, the higher its tendency to get adsorbed to GAC. Polar compounds are typically not removed by adsorption. So which of them are correct? Option A, C, and D. Any other answer? So option A is definitely correct because it's a heterogeneous media for adsorption. That is fine. Then B is not correct because not only natural or no synthetic organic compounds can also be removed. Okay, it depends on the molecular size or the polarity or the solubility. Okay, it's not about synthetic or non-synthetic. Then third one, see, the more hydrophilic a compound is. So what do you mean by hydrophilic? What does that mean?
It hates water.
It hates water or it loves water?
No, it hates water. It doesn't want to get solved with water, so it hates water.
No, it's not hydrophobic. So phobia
Oh
is
yeah.
like
No,
fear.
then this one loves the water.
Yes. So if it's water loving, then it will try to stay in the soluble water in the water form. Okay. It will not get adsorbed to GAC. So option C is incorrect. Then polar compounds are not typically removed. That is true because non-polar hydrophobic compounds will get easily adsorbed to the GAC. So just be little careful with the words. So polar, non-polar, hydrophilic, hydrophobic. Okay, so hydrophilic is water loving. So option A and D are correct. Okay. Reverse osmosis membrane fouling occurs due to chemical scaling. True or false? So true. Nothing much to think about it. It will be true. Next, match the following. So we have to match the characteristics of physical adsorption and chemical adsorption. So there are six characteristics given. So please let me know what is for A, what is for 1 and what is for 2. So what will be correct for physical adsorption? So one by one, can someone tell me? For physical adsorption, we know it is reversible, definitely.
Common type of adsorption
It's a common type
mechanism.
of adsorption, okay. And if it is common type, then and reversible, so it is non-specific binding. Okay, it won't be very specific. So then coming on to the chemical adsorption, it is specific exchange of electrons, maybe some pi-pi bonding or whatever. Then typically it is non-reversible and rarely used in water treatment. So most of the adsorptions are physical adsorption rate mainly. Okay, so option A is the correct answer. Right? Moving forward. Okay, I hope you are able to see this clearly. If you are not, just try to zoom in, or shall I zoom? Okay, let us see the question. Match the following with the reference to the compounds, reference to components of a synthetic ionic resin. Okay, so in the first one we have a COOH group, carboxylic group. Then we have a ring kind of structure. Okay, aromatic ring, and then we have a chain. Okay, so just so even if you don't know anything, if you have not studied also, it will be easier, because by the name only it can give you the answer. So backbone group means there should be a long link, okay, a long chain, something like that, so that it provides the base or the backbone to the structure. So definitely third option, where we can see a long chain of carbon. Okay, so that will be the backbone group. Then cross linking, so we can see that this aromatic compound is linking two different chains. Okay, here it is linking two different chains, so that is a cross linking group. And exchange group, COH. Okay, so from here some exchange can happen. Okay, so this group will be removed, some other group will come and get attached, so it is an exchange group. So option B is correct. Next problem. The correct sequence for attraction to a typical ion exchange resin for calcium, magnesium and strontium will be strontium greater than calcium greater than magnesium. The affinity of ion exchange material is higher for ions with smaller hydrated radius. So you have to select the correct option here. So you have to just visualize the periodic table. Okay. So which of the compounds have the largest ionic radius? So here one thing is that the charge is same. So all for strontium, calcium and magnesium, the charge is same. So charge wise, same affinity. Now comes what is the size of the size of the element. Okay. So if you see the periodic table, the largest ionic radius will be for strontium. Okay, whereas the smallest hydrated radius will be also for strontium. Okay, so don't compare the ionic radius. We have to always compare the hydrated radius. So after hydration, strontium will have the least radius, then calcium, then magnesium. Though the ionic size of magnesium is the least, followed by calcium, then strontium. So that thing you have to take into account. Next. So option C is correct. Okay. So I think this is the same problem. So I hope we can skip it. Okay. We have already solved a very similar problem. So here just the concentration has been changed. Rest is the same question. I'll move forward so you can cross check it later. The correct answer is 35.8 milligram per liter. So it is similar to our second problem. Okay. Select the correct statements regarding chemical and physical adsorption. So, yes, Preeti, you want to ask something?
So the previous problem, will we come across a problem where equilibrium concentration is asked?
Here?
Yes, sir. Here, the carbon dose is asked in this question, right?
Yeah.
So instead of if the carbon dose is given, is there a problem with where equilibrium concentration will be asked?
Yeah, it
Like,
can be asked. Yeah, I think if I have a question like this, it can be asked actually because we have several equations, so it can also be asked the equilibrium concentration. You have to just back calculate it.
yeah, but will we be able to? We will have a nonlinear equation, or how is
Uh,
it?
okay, let me check if some question is there. After framing the question only we can see. So you are
Yeah.
asking that there will be more unknowns, right?
Yeah, c to the power of 0.365.
Haha, so okay, you are asking that the power thing will cause a problem.
Yeah, yeah. Will
Why?
it cause a problem, or
No, why?
how will we have the equation?
So if the power goes to the other side, what will happen? If suppose you have an equation where c is to the power of 0. Suppose x to the
365
power of 0.365. If you take
plus
it to the
c
other
total.
side, what will happen?
No, you have two non-unknowns. One is C tolvin,
Okay.
and then again C tolvin to the power of 0.365, right?
Uh, okay, you are saying okay during the mass balance thing, right? Yeah,
Yeah.
yeah. But yeah, I think if you have a scientific calculator, you can do in the
Okay.
equation thing. Uh, yeah, I think in a scientific calculator it can be done. I understood your point.
Okay.
There will be two uh, terms, one with the
Yeah.
power of 1, one with the power of 0.365.
Yeah.
Okay.
Maybe we have to guess, or
No,
I
but
don't
yes,
know.
but in your final exam, that type of problem won't be asked where you have to guess
Okay.
anything. Okay, so
Okay.
don't worry about it. But I am just thinking practically how to solve it if
Yeah.
it happens. Yeah. Okay. Let me check. If I find some answer, I will let you know. Okay.
Sure. Sir. Thank you.
Sir, you can also check like you will be given like four options, and from one option you can
Yeah, that is. But mostly these questions will be numerical type, so you won't have options here. It can be also there, right? It can be of numerical type, so where options are not given. So I don't think those kind of questions will be asked. So
because there's two unknowns. Like there's a mathematical approach for it, like
yeah.
Newton-Raphson method. I guess it's so
Yeah,
complicated.
I got your point. That point I got your point. But in your exam, I don't think you have too much of time to solve like this. So don't worry about it. You're in your exam that won't be the case. You will be given, I think, direct questions only. Okay. But yeah, if in some other places you have a problem like this, then you have to solve by that method. Okay. So I hope you will solve this problem. If I'll see if there is any problem where equilibrium concentration has to be found out. If I get any problem like that, we will solve it in the extra class. We'll have next week. So also please remember we will have the week 12 class on this Thursday. Okay, day after tomorrow. And the timing is not 7 to 9, it is 6 to 8. From 6 o'clock it will start. So I hope it is fine for all of you. So week 12 lecture we will have on Thursday 6 to 8, and then on next Tuesday we will have the final session that will be an extra class. So some of you have already uh, uh, asked me to solve a particular kind of problem. I will add this problem also there. So those problems can be taken up, plus some problems which we did not complete in our regular class or was given for you to think to work it out by yourselves. So those problems we will take up and we will solve it. Okay. I hope you have all registered for the examination for the certificate course. So okay, so this is also the same problem, so I'm just skipping it. Okay. Select the correctly matched pairs regarding causes of adsorption. Dislike of water phase, hydrophobicity, van der Waals forces, surface charge interaction, electrostatic forces, physical attraction, chemical forces, pi and hydrogen bonding. So which of them are correctly matched? Okay, so yeah, A and D are correct because we just discussed. So hydrophobicity is water hating or dislike of water phase. Then van der Waals forces are physical forces, not necessarily based on the surface charge interaction. Okay, it can be a dipole-dipole. Okay, uh, attraction. Okay, so these are weak physical forces, not related to the surface charge. Whereas electrostatic forces are based on the oppositely charged species. Okay, so electrostatic forces are for charges, and then chemical forces definitely it is a pi or hydrogen bonding. So A and D are correct. Okay, so this problem also we have seen. I think the same problem is there. So let me skip this. Select the particles which are specifically removed by nanofiltration process but not by filtration processes of higher filtration or pore size. Algae, protozoa, bacteria, small colloids, divalent ions and dissolved organic matter, monovalent species. No, so we are asking which is only removed by nanofiltration, not by the other filtration processes of higher sizes, only by nanofiltration. So we have microfiltration, ultrafiltration, nanofiltration, and reverse osmosis, right? So, so what is the typical size of a bacteria? Can someone tell me what is the typical size of a bacteria? Any idea? How big do you think a bacteria is? Or if you have worked in environmental labs, so generally, if you want to remove the bacterial biomass, okay, from our sample, what size of filter do we normally use?
Should it be less than 0.1 micrometers?
0.1 microns. No, you are saying the size of the filter or size of bacteria?
Size of the filter.
Yeah, so generally we don't go up to 0.1, we keep it up to 0.22. So 0.22 micron is the standard filter size that we use. So anything greater than that will be removed. So bacteria sizes are generally in the 1 to 2 micron range. Okay, so this can be removed by ultrafiltration. Then small colloids can also be removed by ultrafiltration, whereas divalent ions and dissolved organic matter divalent charge ions can only be removed by nanofiltration, only in nanofiltration range, whereas monovalent species are removed by reverse osmosis. So the correct answer is option C. Okay. Then again match the following. So we have electrodialysis, reverse osmosis, nanofiltration, thermal distillation. So just by the name only you can answer this. So electrodialysis already, so obviously some electric voltage should be there. So option C is correct. Reverse osmosis, movement of water from low salt concentration to higher salt by applying pressure. Okay, generally from high to low concentration we go, but from low to high, if it is going by applying pressure, it's a reverse osmosis. Then nanofiltration, it is okay. Operation challenges are scaling and fouling. Then thermal, obviously some heat will be involved. So that means uses heat to convert the water into vapors. So option B is the correct answer. Right? Next question. Select the ways in which both iron and manganese removal can be done. Lime soda ash softening below 9.8 pH, chemical oxidation, aeration, lime soda softening above 9.8 pH, or sequestration. So here the only uh, concern will be about, I think, aeration, because though iron can be easily removed by aeration, manganese generally is not fully removed by aeration. Okay, it is partially removed, so aeration will not be the correct there. Whereas chemical oxidation, lime soda ash softening above pH 9.8, and sequestration are the correct options. Okay, so B, D, and E. So generally those are the correct options. Okay, we will not consider aeration because it will not fully remove the manganese. Okay, another one numerical. As a result of effluent chlorination, the amount of chloroform formed was found to be 0.12 milligram per liter. How much powdered activated carbon will be required to treat an effluent flow rate of 400 meter cube per day to reduce the chloroform concentration to 0.05 milligram per liter? The Frederick adsorption isotherm coefficient for chloroform are Kf is equal to 2.6 milligram per gram by liter per milligram to the power 1 by n, where 1 by n is 0.73. So you have to find out what is the concentration of activated carbon here. Anyone with the answer? Zero point 0.026 milligram per liter. So actually 0.026. So have you also incorporated the flow rate? Because there is a 4,000 meter cube per day of flow rate also there. Not 107. Okay, we'll see how to solve this. So we can do it by the approach like uh, so we know that QE that we generally calculate. So it is one is based on the Freundlich equation. Okay. Also QE will be equal to the volume by mass, okay, into the initial concentration minus the final concentration. So this is another. Okay, these are the two equations we know for QE. Okay. So now what we can do, if you just equate both QE, you will get something like volume by mass will be equal to the Kf C to the power 1 by n divided by C naught by C. So you can just put in the values. So you'll get VYM somewhere around liter per gram, or M by V, that is the mass per volume, as just the opposite of it, 0.24 gram per liter. So directly you got the gram per liter. So for 4,000 meter cube per day, PAC required will be this value into the flow rate. Okay. Then I will change liters to meter cube and change gram to kg. So you'll get something around 960 kg per day. Okay, so 960 kg. So this is another approach. I think by the previous approach also we can find out. So did you solve it by the other approach, like how we do by mass balance?
Yes, sir. The other approach.
So we were getting some different. Are you get? Is your calculation correct, or some part is missing? Because I think both of them should give the same answer. Uh, I
I
think.
might have gone wrong somewhere.
Okay. Okay. Anyway,
Yeah.
but this is another approach I'm saying. So directly instead of mass balance, you can equate these two equation and get the answer. Okay. So both will give the amount of dose of adsorbent. Then just multiply with the thing. Okay. Uh, yeah. So. So 960 per kg per day is the correct answer here. Next, a fixed bed activated carbon adsorber has a fast mass transfer rate, and a mass transfer zone is essentially a sharp wavefront. Assuming that the following data apply, determine the carbon requirements to treat a flow rate of 1000 liter per minute and the corresponding bed life. Compound to be treated is trichloroethylene. Initial concentration is 1. Final concentration is 0.05 milligram per liter. GAC density is 450 gram per liter. Friendly capacity factor KF is 228. Friendly intensity parameter is 1 by N 0.62. And EBCT is the empty bed contact time is 10 minutes. Okay, and ignore any biological activity. So how much carbon will be required? Okay, so apart from that, it is a kind of design problem for any carbon absorber. So you have to find out how much GAC that is required. Okay, and then also how much volume of water will be treated and what is the bed life. Okay, we have a carbon bed, so what is the life of bed that we can find out. So it's like a designing problem. So first just calculate what is the uh, dosage. Just tell me what is the dosage. So you can solve by any approach, either whatever I have shown you in the previous problem, because both are ultimately the same. It's just the way of writing it differently. Both are ultimately the same equation. Okay. So what is the dosage in gram per liter? Let me know in gram per liter. For 44 gram per liter. I think the value is too high.
So we use the same equation, right, for finding out the carbon which is adsorbed as Kf into Ce to the power of 1 by n,
Yes.
and that is 0.044 mg per gram. Is that right?
Okay. No, I have not calculated like that way, but okay, let me just calculate. One minus, I think Okay, I think one mistake that we are making here is in this problem it is, yeah, I think the answer which I have is wrong. So let's just let's just solve it in the same way. So I'll just tell you the approach. Okay, so first we will calculate the uh, milligram per liter, okay, or rather gram per liter of GAC. Okay, so yeah, I think something like that only will come. Yeah, because in my answer there is some calculation mistake. So let's say, but 22 gram per liter is very high for dosage. Okay, per liter if 22 grams are required, that is actually very high for an adsorbent dose. Generally it will be 22 milligram per liter, something like that. Okay, so let's for now, let's assume that the answer is 36 milligram per liter. Okay, let's say the dose is 36 milligram per liter. So I can just tell you what are the other steps that we have to do. Then the next step was to find out the mass of GAC in bed. Okay, so we have something called at EBCT, that is the empty bed contact time, that is given as 10 minutes. So how much of GAC will be required? So that will be the volume of the bed into the density of GAC. Okay, so that we have to find out. So volume of bed, so we know that the flow rate is 1000 liter per minute. Okay, into the time. Okay, so that will give you the volume, that is 10 minute. So EBCT is 10 minute is given into the density. So that is 450 gram per liter. It is given in the question. So we'll get something as 4.506 gram. Okay, so that much mass of GAC in the bed is required. Okay, so how much volume of water can be treated? Okay, so volume of water treated will be equal to the mass of carbon. Okay, how much carbon mass that is required, mass of carbon for the given EBCT, that is 10 minute. Okay, so if empty bed contact time is increasing, the mass of carbon will also increase, divided by the rate of utilization. So what is the rate of utilization? This dose is the rate of utilization. So what will be the case? There is 4.536 gram divided by 0.036 gram GSE per liter. Okay, 36 milligram or 0.036 gram. So that means 1.26 into 10 to the power 8 liters of water can be treated. So that's how we calculate the volume. So 2 points. One is how much mass of the adsorbent is needed in my bed. So that depends on the flow rate into the EBCT, okay, into the density. Okay, so that will give you the mass. Then mass by dosage will be giving you how much volume of water that can be treated. Okay, and the final thing is the bed life. So bed life, that is the volume of treated water divided by what? What will give the life of bed? Can someone guess? How can we get the bed life? So we have a volume of water. If I
Break
div
point or
sorry,
the break point, you mean?
uh, not the break point. So just think. So bed life will be something in time. Okay. So let's say days. Okay, we need a quantity in days. Okay. So we have something volume. So let's say it is some meter cube. Okay, or maybe liters. So if we divide by what parameter, we will get days. Simple, just by
Flow rate.
flow rate, right? So it will be divided by the flow rate. So we have a volume of water, at how much rate it is coming will tell me how, in how many days my my bed will be used up. Okay, so that will be my time. Transfer 8 liter divided by 1000 liter per minute. So I can change into this days. So it is 87.5 days. So after 87.5 days, we have to change it or we have to regenerate it. Okay, so these are the design criteria points for the GSE column. So bed life, how much volume of water that can be treated, how much mass of GSE that is required. The first part remains the same. The dosage part remains the same. Okay. Actually, in the in the problem, this KF. So this is the value of KF. I think most of us just did it like QE is equal to KFC to the power 1 by n, right? So KF value itself is 228 to the power of 1 by n. So QE, your QE value will be equal to KF CE 1 by n. So here KF itself is 228 to the power 0.62. Then you have to take 1 milligram per liter and take to the power 0.62. So this is how you have to find out the QE. Did you solve like this?
No, sir.
No, yeah. So
But
that is the mistake that we were making. Okay. So the KF value is given here. It's not the QE value. If you see here, this is the value of KF, not the CE value. Okay. And similarly, the previous problem also. Is there any doubt? Okay. So here also, KF value is 2.6 to the power 1 by n. So it will be 2.6 to the power of 0.73 into the concentration to the power of 0.73. So that will be the equilibrium equation. So that was the mistake that we were making. Yeah, I understood it now. So you have to solve it like this because KF value is only given. Okay, so one more problem we have for today. Let's solve this. So yes, so a treated wastewater with a flow of 1000 liter per minute is to be treated with PAC to reduce the concentration of residual organics measured as TOC from 5 to 1 milligram per liter. The friendly adsorption parameters are developed as below. So assuming that the following data apply, determine the PAC requirements to treat the wastewater flow. If PAC cost $0.5 per kg, estimate the annual cost of treatment. Okay, assuming that PAC will not be regenerated. So what is the annual cost of treatment? So please try to solve it. So what is the dose that you are getting?
So I'll first say how much milligrams per gram of activated carbon. You told that formula, right? Kf to the power of 1 by n
Yeah.
E
No, no.
into.
Yeah. So after that, you will find out the dose, right?
But that even that is too high. Like it's like
That is too high, right? Yeah,
yeah,
even
22,500.
mhm.
It's
Yeah, even I am also getting the dose as very high. Okay, I think these answers are little on the higher side. Uh, okay, anyway, so whatever dose you get, so you don't have to worry about the answer for now for this question. So whatever you dose you get, you have to just multiply with the flow rate, okay, and then multiply with the number of days. So per year you have to find out. So multiply with number of days and then the cost because it will be per kg. So dollars. So that much dollars will be. So this is all related to the dosage here. Okay, most of the problems are related to find out the dosage, like the QE, then the dose, and then some more extra parameters. So same kind of problems are there. Okay, so yeah, that's all for today. I think we have solved all different types of problem, but I will check if is there any problem where we have to calculate the equilibrium concentration. Okay, CE. If I get something like that, we will solve it in the extra class. Okay, and okay, any other recommendations for the extra class? I got few more points from mail, but is there any other recommendations? Those who are here, can you tell me any other topics? Nothing? Yes, Preeti, you are saying something?
so. Is it okay to look into ion exchange design a little bit? Is it
Ion
possible
exchange design?
or
Yeah, we can do that. Okay, we can do that. Ion exchange design also, I will get some design problems. Okay, fine. Ion exchange design I will add because there are some problems related to that. It is actually ion exchange design problems are also similar to that these adsorption problems. Okay, more or less the same kind of calculation is there, but yeah, we can look into that.
just like how do we choose the right ion exchange resins, and like how do we design it? Basics, not too much, but just the
Okay,
basics.
basics. Uh, okay, then you are talking about the qualitative part. I was thinking in the numerical side, how to
But
change the.
numerical side also, if it is so, ion exchange resins can also be used to remove hardness
Yes,
from the water, right?
yes.
Mainly hardness.
Actually, not much many difficult problems are there. That same volume to this flow rate conversions, then mass to density conversions. Only these type of problems are only there. But I will check if I am getting something. I will look into this.
Okay, sir.
Okay,
Okay, sir.
thank you for
Thank you, sir.
telling
Yeah.
me. And also, I think we have not solved much problems related to the digestion or the digestion related in the wastewater part. So maybe we will solve some problems related to that. Okay, because in the sludge management thing, we haven't looked into like how the volatile or the fixed solids, how they are changing and how to do the calculations based on the specific gravity and all. So those problems also we can take up, I think. So that I will also add. So again, anything else comes to your mind, you just drop me a mail. Okay. So then we can look into that. Okay. So that's all from my side for today. We'll meet again day after tomorrow uh, from 6 to 8 p.m. So if you have any queries, you can stay back or else you can leave the session. So thank you so much.
Thank you, sir.
Thank you. Hmm.